In our last lecture, we started to talk about non-ideal reactors and how convection inside of plug flow reactors and CSTRs might not happen ideally. And because of that, we have deviations from the behavior that we saw earlier on in our semester. And so we started to zoom in on one such setup, which was a CSTR with both bypass and dead zones. And so we're going to start lecture today by solving an example that has those two things in an operating CSTR. And to do that, we're going to consider the simplest reaction that we can. A goes to B in a 12-liter CSTR with a K1 equal to 0.325 inverse minutes. The initial concentration of A is 1 molar. The volumetric flow rate is 2 liters per minute. Experimental data suggests that 10% of the flow is immediately bypassing the reactor and that 20% of the reactor volume is comprised by dead zones. Find the conversion leaving the reactor and compare it to the conversion leaving an ideal CSTR with no dead zones or short circuiting. Now, I'm going to start the solution today with the second half. Let's solve the ideal case first, and then let's take a look again at what a flow diagram might look like for a CSTR with both dead zones and short circuiting, and then we'll solve this problem with the information that we have. Now, if you remember, for an ideal CSTR, we always started with our mass balance, right? Which is just in minus out plus the reaction is equal to accumulation. And our CSTRs are going to operate at steady state. And so this gives us simply in minus out plus reaction is equal to accumulation. Or if we actually write it in terms of flow, this is just FA0 minus FA plus RA times V is equal to 0. And we also can write the flow as CA0 times V0 minus CA times V minus K1 CA times the volume is equal to 0. Now, if this is a liquid phase reaction, or if delta N is equal to 0 and it's isothermal and isobaric, you have the initial volumetric flow rate and the final volumetric flow rate are equal to each other. So I'm just going to get rid of the V naught here right after CA0. So we have CA0 times V minus CA times V minus K1 CA times V is equal to 0. Now, a thing that we would often then do in a problem like this is get things in terms of conversion. That's the variable that we're after at the end, right? So we have our mole, we have our rate law, we have our mole balance, and now let's get things in terms of the variables we want. Well, we know that this is CA0 times V minus CA0 times 1 minus X times the volumetric flow rate minus then K1 times CA0 times 1 minus X times the volume. And that's equal to 0. And remember, earlier in our semester, we defined the residence time as the volume divided by the volumetric flow rate. So I'm going to go ahead and divide everything through by the volumetric flow rate and get CA0 minus CA0 times 1 minus X minus K1 times CA0 times 1 minus X times the residence time is equal to 0. Okay. And these two are going to simplify because this is just CA0 minus CA0 plus CA0 times the conversion, right? So those two terms go away. And we're just going to get CA0 times the conversion minus K1 times CA0 times 1 minus the conversion times the residence time is equal to 0. And then, of course, the CA0s are going to cancel. So we get the conversion minus K1 times 1 minus X times tau, is equal to 0. Okay. And we want to solve here for the conversion. So to do that, let's FOIL this out, right? And you get X minus K1 times tau plus K1 tau times the conversion is equal to 0. And then you get the conversion times 1 plus K1 tau minus K1 tau is equal to 0. And then finally, right, we can solve for the conversion, and that's just K1 times tau over 1 plus K1 times tau. And this is exactly what we did earlier on in the semester. And we know K1, and we can find tau. And so if we know that tau is the volume divided by the volumetric flow rate, so here in our problem, right, we know that we have a 12-liter CSTR, and we're given a volumetric flow rate of 2 liters per minute, right? And so that's equal to 0.325 times, and then tau then would be, and let's just get the units right. Right, that's minutes to the -1. Tau here is 6 minutes divided by 1 plus 0.325 times 6. Right? And that gives us a conversion of 0.66. Okay. So is this okay with everybody? Hopefully, yes. So now let's consider the case where we have short circuiting and dead volume. And we actually started to look at this in our last lecture and what a 2-parameter model to describe that system might look like. And so if you remember, what happens here is that we have this initial flow rate in at our initial concentration, and we split the flow. So we define this term beta, which is the portion of the volumetric flow rate that bypasses the reactor. And so we called this VB, and so that was equal to V naught times beta. And then the flow that actually goes through the reacting zone of our reactor is the rest of that, right? Which would be V naught times 1 minus beta. Then we define this term alpha, which is the portion of the reactor that's utilized, right? Or not comprised of the dead zones. And so alpha then is this Vs over V, which means that the dead zone volume, V sub D, is 1 minus alpha times the volume. So you basically have the portion of the volume you use, and then the portion of the volume that is comprised by dead zones. And what we said we were going to do when we solved this problem, here I'll leave this for a second and just talk so that way you guys can write it again if you'd like to, is that we were going to solve the problem here with 2 mass balances. The first one that we would do is around the reactor here. Okay. So we'll apply the same equation that we did just a minute ago for the ideal reactor case. We'll simplify the terms that we can, but just remembering that that mole balance around the reactor has a different volumetric flow rate going through it, and it has a different active reactor volume. And we're going to take those things into consideration, and we're going to get things in terms of alpha and beta, the 2 things that we defined. Then after we have a look at that, we're going to get an expression really for just the concentration of A that's leaving the active part of our reactor, or CAS. And then that has to remix with the short-circuited part at steady state. So the second part of our solution here is going to involve a mass balance right there at that mixing point. Okay? All right, so let's do those 2 things. Let's first do the mole balance around the active part of the reactor. Then we will solve the mass balance here. Okay? Now, if we want to do this while actually having a look at what's going on in the reactor, so we have in minus out plus the reaction term is equal to accumulation. Well, entering the reactor is the initial concentration of A, right, Ca0, but now times Vs. right? This fraction that is not going through bypass. Then leaving, we have CAS, which is the concentration leaving the reactor, or the active part of the reactor, times VS, plus the reaction term. And so our reaction term here is K1 times CA in the active part of the reactor times the active part of the volume is equal to the accumulation, which is equal to 0. So is this okay with everybody, or does anybody have a question here about how I got that from the diagram? Okay, if not, then I'm going to move this up and continue. So what we want to do now is get this in terms of alpha and beta. So we know VS is just V0 times 1 minus beta, right? Then that's times CA0. Then minus V0 times 1 minus beta times CAS minus K1 times CAS times alpha times the volume, right? That's equal to 0. So now we have our mass balance in terms of these two parameters, alpha and beta, which is what we wanted. Now, what we actually want to solve for here is CAS. So let's group those terms. And it's one of the nice things about an algebraic expression like this for a CSTR. It's fairly straightforward to do this. So we get V0 times 1 minus beta times CA0, then minus CAS times V0 times 1 minus beta, then plus K1 times alpha times V, right? And that's equal to 0. And we then can solve for CAS, and that's equal to V0 times 1 minus beta times CA0 divided by V0 times 1 minus beta plus K1 alpha times the volume. The other thing that I could do is I could divide the right side by V0, both the numerator and the denominator. And if I did that, right, you would get you'd get rid of the V0. That'd be 1 minus beta times CA0 divided by 1 minus beta plus K1 alpha times V over V0. And V over V0 is just the residence time for our reactor, right? So then that is just times tau. Okay. All right. So what we're going to do is just stick a pin in this for a second, right? We have the concentration of CAS. Okay. So now let's look at our mixing point, right? And to do that, let's go back up to the diagram here. So when we look at our mixing point, we have 3 streams, right? We have 2 coming in and we have 1 that's leaving. Okay. So we have to take all 3 of those into consideration. And the stream that's coming in here is the bypass stream. The stream that's coming in from the reactor has the fraction that went through the active volume. And then the volumetric flow rate leaving is actually the full volumetric flow rate because they've come back together and it's at the final concentration of A. And this is the thing that's going to end up giving us what the actual conversion is inside of this reactor. So at this, thing that I've called the mixing point, we have a relatively straightforward mass balance, right? In minus out, there's no reaction, is equal to 0. So this just becomes CA0 times the volumetric flow rate that goes through the bypass plus CAS times the volumetric flow rate going through the reactor minus V0 times CA is equal to 0, right? These are the 2 streams in. This is the 1 stream out of that mixing point. And so what we can do then is just solve for the thing that we're really after, which is CA. And so CA just equals CA0 times VB plus CAS times VS divided by V0. Okay. And if I split this into two terms, CA just becomes CA0 times VB over V0 plus VS over V0 times CAS. Now remember that VB over V0, right? That's just the portion of the flow that goes through bypass. So that's just CA0 times beta. And VS over V0 is the portion that doesn't go through bypass, right? That's 1 minus beta. Then times CAS, which is what we actually solved for just a moment ago. Okay. So that becomes 1 minus beta times 1 minus beta times CA0 divided by 1 minus beta plus K1 alpha times tau. Okay. If I divide through by CA0, right, that's just CA over CA0 equals, now if we look at this, the first term, of course, is just beta. Then this is plus 1 minus beta squared times CA0 divided by 1 minus beta plus K1 alpha times tau. Okay.
A question. Should the CA not be gone from the second term?
Oh, thank you very much. Yeah, I'm sorry about that. You are correct. Good catch. Very good catch. All right, great. So then let's find alpha and beta from the information that we're given in the problem. So remember, alpha is equal to the active part of the reactor divided by the actual volume. So we're told in the problem statement that 20% of the volume is dead zones. So then the active volume is 12 times 1 minus the portion that's dead zones divided by the volume. And right, so that's equal to 0.8. So we utilize 80% of the reactor volume. And then we're directly told in the problem that 10% of the volumetric flow rate goes through the bypass. So B then is equal to 0.1. Okay. Perhaps the last step in solving this problem is that we know that if FA0 is FA0 times 1 minus X, just to get things in terms of conversion, right? Well, CA times V is CA0 V0 times 1 minus X. And we were already told here that the volumetric flow rates are the same. So CA over CA0 just equals 1 minus X. So 1 minus X equals beta plus 1 minus beta squared divided by 1 minus beta plus K1 alpha times tau. Or solving for the conversion then, the conversion equals 1 minus all of this. So beta plus 1 minus beta squared over 1 minus beta plus K1 alpha times tau. Okay. So then in this problem, our conversion then is just 1 minus 0.1 plus 1 minus 0.1 squared divided by 1 minus 0.1 plus K1, which was 0.325, times alpha, which was 0.8, times tau, which was 6. And we already know that the units here and here cancel, so I wrote them unitless. And from there, we can calculate the final conversion. And X equals 0.57. So you can see that the dead zones, which reduce the effective residence time, and the short circuiting severely limit our reactor effectiveness, right? That we go from a conversion of about 0.6 to 0.57. And if you think about this, I mean, that's a loss of about 15% of the conversion. And so, flow and the type of flow happening inside of a reactor can have a very significant effect on the conversion that you're able to achieve. Now, I did do the same calculation with a longer residence time. And so I also solved this when tau was equal to 12, and we could get there either with a larger reactor, or we could do this with a different flow rate, right? So in this case, let's just do that, right? Where that was just 1 liter per minute. And in that case, the ideal was equal to 0.8. And we'll call this X real, right? The real conversion was basically equal to 0.7. And so again, it's like about a 12% loss or so. So even when we had a slightly higher volumetric flow rate, the loss was approximately the same. So this is an example of how, yes, you get to a higher conversion, but the effect is the same. So what you can do then in a real reactor is either to, at the beginning, modify the shape. So one thing that's done in real reactors, instead of having boxy corners, is you will see some CSTRs have rounded bottoms. And this is exactly for this. Another thing that you can do, and it's something that we don't really talk about in our class, is you could design the impeller for improved mixing. And in fact, I've taught junior lab in the past, and we did this. We built our own CSTRs, and then we measured the effectiveness of the mixing, and then the students then went and designed new impellers. We 3D printed them, and then we tested the mixing again. And the idea here was that you would iterate a few times until you got to something that approximated ideal mixing inside of a CSTR. So it's a pretty cool project. So you have to think about it. It can be impeller design, whether it's a different shape, different baffle geometry, multiple impellers, although you can have vortexing with multiple impellers. That's just when the fluid just spins around the outside. It actually doesn't mix. And you also can change the reactor shape. So there's all sorts of different options that you can have to improve the flow of a CSTR, or to improve the flow pattern even in plug flow reactors and others, okay? Now, at the beginning of this problem, we were told alpha and beta, essentially, right? I mean, if we look back at the problem statement, right, we were told that, look, that's the dead volume, and that is the portion that bypasses the reactor. But how do you find that, right? I think that's a really logical question. And the most common way to do this is to use a tracer. And a tracer is something that you feed at a known concentration, and you measure the concentration of that species leaving the reactor. And actually, often you measure it coming into the reactor and leaving. And you make this observation as a function of time. And from that observation, you determine what alpha and beta are in this model. So let's do that here. So let's say that we have this experimental data, and we have a tracer with an inlet concentration of 2 milligrams per liter, and using the data, determine the parameters alpha and beta. I'm sorry, the concentrations are missing all their decimal points, by the way. That should be 1.00, 1.33. So let me just add those really quick. Yeah, so that's, sorry for the typos there, guys. All right. And so now, using the data in the table below, or actually, maybe a better thing to do is let's just change this to 2000, because I also did calculations later. So I apologize for that. So we're going to feed it at 2000 milligrams a liter, and we then measure the concentration as a function of time. Now, because we're going to do this, we're observing the portion of the reactor operation that does not exist at steady state. And so if we're doing this in a non-steady state way, we're going to have to solve a non-steady state mass balance, which we haven't done a lot of this semester. But it starts in the same place and it starts with the same system. So to show that, let's think about what's happening when we feed a tracer. Well, if we look at a reactor, or from a reactor perspective, we actually can draw this exactly the same way that we did in our previous example problem. The only difference now is that we have some initial concentration of a tracer that I'll call CT0 at an initial volumetric flow rate. And this is also CT0 at the bypass volumetric flow rate. And we still have this entering the reactor also at the initial concentration. But at the beginning of operating the reactor, right, which has some portion that's a dead volume and some portion that's an active volume, that the concentration is zero. It's just filled with a liquid, right? You haven't put any tracer in at the beginning. And so when you start to measure the concentration coming out of the reactor, it's going to start very low and it's going to start to approach the value that you fed, right? CT0. And of course, coming here is still this volumetric flow rate. So we're going to do the same sort of mass balance that we did just a minute ago, right? And say in minus out plus reaction is equal to accumulation. But in this case, there is an accumulation term and there's no reaction, right? Because it's a non-reacting tracer. In fact, the tracer doesn't have to even be one of your reactants. And there's a lot of ways that you can measure concentration. So you could do it by chromatography. You could do it, let's say that you even were doing like a food dye type experiment. Well, you could do it with UV vis spectroscopy, for example, where you're just looking at the color intensity as a function of time. So there's a lot of different ways that you can do this. So entering the reactor, right, we're coming in at VS times CT0, and we're leaving at VS times CTS, right? This is the same sort of approach that we took a minute ago, and that equals the accumulation. So it's the accumulation of the number of moles of the tracer per time. And now remember, for us, right, NT is also the concentration of the tracer times the volume, right? And that's VS dt. And if we treat the active volume as equal to a constant, that just becomes VS times dCTS dt. Okay. And we're going to use the same definitions that we used before, so that alpha was equal to VS over V, or V, I guess maybe I'll leave that the way that it is. We'll use it that way. And we also defined beta as VB over V0, which of course then meant, just like before, that VS was equal to V0 times 1 minus beta. Okay, so let's put these in our mass balance. So VS, as I just said, is V0 times 1 minus beta times CT0, then minus V0 times 1 minus beta times CTS. And that's equal to VS, which we already said was alpha times the volume, times dCTS dt. Okay. So one of the things I can do here is divide through by V0, okay? And when you do that, you get 1 minus beta times CT0 minus 1 minus beta times CTS equals alpha times tau times dCTS dt. We also have this 1 minus beta term that is the same for these two, right? So this can just be 1 minus beta times CT0 minus CTS is equal to alpha times tau dCTS dt. And we know we're going to have to integrate this. So we got to get everything with CTS on the same side of the equation. And when we do that, right, this just becomes D of CTS divided by CT0 minus CTS equal to 1 minus beta over alpha times tau times dt. And there are, several ways that you can go about solving it from here, right? You know that this is just dx over like a minus x, right? So that's one way to do this. I chose instead to just divide this side of the equation through by CT0. And then I would get this thing that's d CTS over T0 over 1 minus, or d of 1 minus CTS over CT0. And that's equal to 1 minus beta over alpha tau dt. And now we're going to take this integral. So we're going to go from 0 to t. And then on the left-hand side here, that CTS over CT0 at the beginning is 0 because CTS is 0 at the beginning. And we'll just integrate this to some CTS over CT0 in the future. And the reason I did it this way is because for me, this log comes out very naturally. So the integral on the left-hand side just becomes minus the natural log of 1 minus CTS over CT0. And we've actually done this integral before. We've actually done dx over, and that d doesn't belong there, but dx over 1 minus x. We've actually done that a bunch of times before this semester and gotten to here. So I thought that that was a pretty straightforward one to do. And that just equals 1 minus beta over alpha tau times time. Or when your book derives this equation, they do 1 minus beta over alpha times t over tau. And I think they do this just to get the coefficients together. And then you can start to compare the real time versus the number of residence times. So then one thing that we can do here is multiply by -1 and take the exponent of both sides. And then this just becomes 1 minus CTS over CT0 equals the exponent of minus 1 minus beta over alpha times t over tau. And then we can get an expression that CTS over CT0 equals 1 minus the exponent of minus 1 minus beta over alpha times t over tau. Okay. And this looks, hopefully pretty familiar. We've had several expressions throughout the course of the semester that look like, even CA over CA0 equals 1 minus the exponent, remember, of minus K1 times tau. And it's kind of like that here, right? So the math ends up working out to be very similar to stuff that we've done before. All right, so let's stick a pin in this for a second. We're going to come back to it. Now we're going to do the same thing we did with the reacting system, and we're going to balance the mixing point. Okay, we're going to do a mass balance right here as well, where again, we have 2 in and 1 out, and they're essentially the same as we had before. So we have CT0 times the bypass volumetric flow rate plus the volumetric flow rate from the reactor, or from the active part of the reactor, times CTS minus the concentration of the tracer that we're measuring times the total volumetric flow rate, and that's equal to 0. And we can solve for CT, right? And that's just equal to CT0 VB plus VS times CTS over V0. And this is the same step we did in the previous one, right? This is just VB over V0, CT0 plus VS over V0 times CTS. So I'm going to divide both sides through by CT0. So I'm going to get CT over CT0 equals VB over V0 plus VS over V0 times CTS over CT0. And the reason I did that is because we have an expression for that we spent all that time deriving just a second ago. So CT over CT0 equals VB over V0, right, which is just beta, and then plus VS over V0, and again, that's just 1 minus beta, times CTS over CT0, and that's 1 minus the exponent of minus 1 minus beta over alpha times T over tau. And I'll close both brackets there. Okay. And so I'm going to FOIL this out. It's not as bad as it looks like it's going to be. So CT over CT0 equals beta plus 1 minus beta minus 1 minus beta times the exponent of minus 1 minus beta over alpha times T over tau. And this thing simplifies, right? This just becomes 1 because you get beta minus beta. So CT over CT0 equals 1 minus beta times the exponent of minus 1 minus beta over alpha times T over tau. And you think, all right, now we have an equation that describes the behavior of our data. Now, how do we rearrange this to easily extract alpha and beta? Now, you could just do a regression analysis, right? Where you have CT as a function of time. You could just divide CT over CT0, and you could even in Excel, right? Use solver, minimize the sum of squares between the experimental data. And we've done that in the past when we were trying to find reaction order and all that stuff from experimental data. We also like to develop methods that we can learn something about the system graphically. So I'm going to do that here. And the first step in doing that is taking this equation here at the top of the screen and just moving the 1 to the other side. And so CT over CT0 minus 1 then equals minus 1 minus beta times the exponent of negative 1 minus beta over alpha times T over tau. Okay. And the reason that I did that is because I really want to incorporate the CT0 into here. So I'm actually going to write the 1 as just CT0 over CT0. And that equals minus 1 minus beta times the exponent of minus 1 minus beta over alpha times T over tau. Okay. And now I'm just going to combine that together. So this becomes CT minus CT0 over CT0. And the other thing that I'd like to do here is I want to multiply this side of the equation and this side of the equation by minus 1. So if I were to do that, right, this would happen to the left-hand side of the equation. So I'm just going to rewrite it that way. So this just becomes CT0 minus CT over CT0 equals, and because I multiplied through by minus 1, that's 1 minus beta times the exponent of minus 1 minus beta over alpha times T over tau. And I really did that because I don't like negatives in front of logs. So I'm going to take the natural log of both sides. And so this becomes the natural log of CT0 minus CT over CT0 equals the natural log of 1 minus beta. Then the log of the right-hand side of this just becomes minus 1 minus beta over alpha times T over tau. And the nice thing that we've done here is that we've separated a term that only has beta and a term that has both alpha and beta. So what we really want to do then with this is we're going to plot the natural log of CT0 minus CT over CT0 versus time. And when we do this, our slope is just equal to minus 1 minus beta over alpha times the residence time. And our intercept is equal to the natural log of 1 minus beta. Okay, so we started this example problem with our data, right? That we had the concentration as a function of time. So the first thing that I did after deriving this expression is to calculate, CT0 minus CT over CT0, and then to just take the natural log. So now we have the natural log that we're looking for of that ratio, and we also have time in minutes. So I plotted those next to each other or against one another, and as expected, got a straight line. Okay, and so the first thing that I did was I picked on the intercept, because we know the intercept is equal to the natural log of 1 minus beta, just like we wrote a second ago. So that means that beta is just equal to 1 minus the exponent of the intercept of minus 0.2085. And we can find then that beta is equal to 0.19. So in this particular example, we have almost 20% of the flow going through bypass. Okay. Now, the second thing that we can do is take advantage of the fact that we know that this slope is equal to minus 1 minus beta over alpha times the residence time, right? Or, alpha, this is really the thing now that we don't know, is equal to minus 1 over our slope times 1 minus beta over tau. So that's equal to minus 1 over negative 0.1157 times 1 minus 0.9 divided by tau in this particular problem. And so we were told here that the reactor volume is 1,000 liters and the flow rate is 100 liters per minute, right? So then tau would be V over the volumetric flow rate, which is 1,000 liters over 100 liters per minute. And that equals 10 minutes, okay? So times 10 minutes, and we find that alpha is equal to 0.70.